Lesson 6b, Evaluate and Graph Polynomial Functions. This is a lesson that's just going to have you think about all the components that go into a polynomial function and how they play a role in what the graph may look like. The first polynomial function is the one where you have an x to the 0 power. Anything to the 0 power is just 1. So you're pretty much just looking at a function where y is equal to a number. And when you graph that, can't graph a straight line. You're looking at a horizontal line going through whatever that number is. So let's say 1, 2, 3, 4, 5, 6. So this might be the function y equals 6. Now you notice 6 is a positive number. So this graph is entering from the left and exiting from the right, both above the x-axis. If I gave you a negative 1, let's say negative 4 or negative 5, then you're going to be down here below. Something else that you want to pay attention to is this guy has a degree of 0. That means that there aren't going to be any zeros or rational roots that fall on the x-axis. Okay, there's not a possibility of any of them happening. The next function we're going to look at is a linear function. A linear function in its normal form would be something like y equals, and you could do like 2x or 4x plus 3. Okay, and what's making it linear is that your x value is being raised to just the first power, which is going to make your degree 1. Again, we're talking about that relationship between the degree and how many times you could touch the x-axis. So a function like this, 4x plus 3, is going to have a slope of 4, and it's going to have a y-intercept of 3. So you'd be looking at something like that. So since our a value is positive, this guy enters from down here in the third quadrant and exits from the first quadrant. If our a value was negative, then he would do more of something like this, where you'd enter from the second quadrant and exit through the fourth quadrant. So we've spent a lot of time with constant and linear functions. We've also been doing quite a bit with quadratic functions. Those are the ones that graph as parabolas. And so they're going to look, excuse the drawing, like a parabola. Again, this one has a degree of 2. It's a quadratic because it's an x squared. Your degree is 2. So you have 2 possible places where you are going to cross the x-axis. Now don't get me wrong, it's possible for it to only touch once. You know, if we did something like that, it would only touch once. Or it's possible for it to not touch at all. But the most number of times that that graph could touch the x-axis is whatever your degree is here. So that's a quadratic. It's entering through the second quadrant. It's exiting through the first. If your a value is negative, it's going to do something more like this, where it enters from the third and exits through the fourth. So all of those functions are ones that we've already looked at, which is going to take us into a new one, which is the cubic function. That's when you have a power of 3. The cubic function kind of resembles, a lot of people call it the Egyptian, because it kind of does a snake pattern. You come up, you cross through, and then you come up like that. So a cubic function, which has an odd degree, will enter and exit from different locations. Even degreed functions will enter and exit from the same vicinity. from above, goes out from above, comes in from below, goes out from below. Odd functions like the linear and the cubic will enter from one side and exit from the other. So we come in from below, we exit from above. We come in from above, we exit from below. So a cubic function, which has odd degree of 3, I've only drawn it here where it only hits once, but it's possible for it to hit a maximum number of times is 3. So there's 1, 2, 3 spaces. This one would represent a negative x cubed function because you entered from above and you exit from below. And then the last one we're going to look at is a quartic. Again, it's an even degreed, so at most times you can hit 4. Since it's even, it's going to enter and exit from the same side, so above, above. And since our a value for this one is positive, we're going to do something like that. Now this one that I'm showing you is showing you 4 different zeros. 1, 2, 3, 4. It's possible that the quartic could very well look like a parabola. You could just do something like that. And so the degree is the most number of times that you could have zeros. Again, this one's entering and exiting from the top, so this would be a positive x to the 4th. This would represent a negative x to the 4th. Symmetry is also a very important part of polynomials. The symmetry, if something has even symmetry, then that means the graph is going to have symmetry around the y-axis. So, for example, x squared has even symmetry, because if you held a mirror up to the left-hand side, it would resemble the right-hand side. Something that has odd symmetry is like the cubic function. This is hard to freehand. Okay, and what that says is whatever you see here, if you carried it around 180 degrees, then you're going to see the same thing here. The reflection is a rotation rather than a left to right movement. Multiplicity is the factor that the exponent that a factor is being raised to. If it has even multiplicity, then that specific factor would be raised to an even power. And what that does is, let's say you were looking at y equals x minus 2 squared times y plus 3. Okay, so this guy's already been factored out. He originally would have been a cubic function. How do I know that? Because here are 2 x's, and then here is the third x. So this is a cubic function. Our a value is positive, so we know we're going to be coming in from down here and going out from up here. You know that you're going to have zeros or x-intercepts at 2 and negative 3. 2, so we're going to put a dot at negative 3, and we're going to put a dot at 2. Okay, you could multiply this out to get it in general form, or if you wanted to figure out what the y-intercept is, you plug 0 in for x, so that would give you negative 2 squared is 4 times 3 is a 12. So you know that it's going to have a y-intercept of 12, which is probably up here somewhere. Alright, and then the way multiplicity plays a role here is I know that I'm going to enter from down here, and when I hit that first 0 of negative 3, since that's an odd multiplicity, I'm going to go through that 0. Okay, I know that I have a y-intercept. And then when I come down here to this 2, This 2 have even multiplicity, so it's going to bounce, but it's not going to cut through. And it could look something like that. Okay, so when you have even multiplicity, you bounce, and right there's an example of that. When you have odd multiplicity, you cross through the function, and that's an example of that there. Okay, so multiplicity also plays a large role. So what you're going to do with your work now is you're going to look at several different functions, and you can come up with the information about those functions. What's their behavior, the end behavior. Well, if this guy's going off, this end behavior goes to positive infinity. And the beginning behavior is coming in from negative infinity. You can talk about the zeros, because in factored form, each of these factors, if you solve them, would be your zero. You can talk about whether those zeros are going to bounce or whether you're going to cut through at them. You can get your zeros are the same as your x-intercepts. You can get your y-intercept by plugging 0 in for x, and that would tell you where you're going to cross the y. So there's a lot of important information that you can pull out of just a simple polynomial expression or equation just by knowing what each of the components of them represent. So let's see how you do with this. If you want some more information on it, then go ahead and look at the PowerPoint and the at-home tutor that is used with your book at the website that you can access through Moodle. Thanks.